So the other part of this, I was debating whether I should do the lecture directly or talk about Josh's stuff, but I think I was reading through the notes that you guys made, and I think there are some good questions being asked, actually. So let me actually pose those questions first. I mean, I wrote down on my notebook, so I'm just going to write a, oh, let's see, 1 second. Yeah, by the way, I also added the slides that Josh has to our Moodle site if you ever want to take a look. So this is the slide. I mean, it's a PDF, so the animation still doesn't work, sorry, but it contains the main contents. So what I want to do is, many of you, I think, asked some questions, and we're going to go through them, of course, but I want to pose those questions early on so we can start thinking about it. So one of the questions, let's see. Yeah, it's a question a few of you asked about, I think. Let's see. I'm just going to type it, write it. So the first question, I think, let's see. Yeah, so I think Gabe asked about it. And then there are 2 other remote students. You probably don't know their name, Houchen and actually, they're both from Baltimore. You all asked about how to give, I mean, I'm trying to paraphrase it, how to give hyperprior to hyperparameters. So those 2 terms start to show up, sorry, in hierarchical modeling. So we've been talking about parameters and priors, right? So parameters are those, so a model has parameters, and then you put priors on those parameters, and then you do the Bayesian inference, go to their posterior. But then once we start talking about hierarchical models, you notice that some of the parameters are going to share the same prior. Right? I think that's the main message that's coming out from the video that we've been watching. So then it becomes, you're going to have what we call hyperparameters. So those are, you can think about their parameters on parameters. So we call them hyperparameters. Okay? And many of them are being shared. How exactly they're shared, I mean, it's actually very challenging to do. But we start to talk about this hyperparameters, the definition. And then, of course, the prior distributions that you put on the hyperparameters, we call them hyperpriors. Okay, so get through these ideas, and then, of course, once you know the definitions of this too, and then Gabe Houchen and Akshay all asked the question, how do you give hyperpriors to hyperparameters? So in the study that Josh did, I mean, he gave us what they used. Some of them are different from what we usually do. If you remember, they have this sigma, which is the standard deviation of the normal. What we've been doing is what? We give a inverse gamma prior to the precision. Right? So what we have been doing is we give precision is 1 over sigma squared, right? We've been given gamma to it, which the main reason why we've been doing that is because of the nice conjugacy. Okay. But you can be more free. You can give other prior distributions to this. So if you remember, I think in Josh's study, not square. I think they simply give a gamma to this. Right? I think many of you commented, which is good, and it's a good catch. I mean, again, it's sort of different from what we've been doing, but it's still, I mean, giving a gamma makes sense because sigma, being the standard deviation, should be non-negative, right? And gamma distribution is guaranteed to be non-negative, so at least that's good too. So that's good to keep in mind. And I wonder, even if you give a different prior distribution for sigma, like say if we're going to give gamma to the precision, I don't know how the result's going to change, but I'm pretty sure, I mean, Josh and his team, they must have reasons why to give a gamma to sigma directly. We can ask him, I don't know. But I'm just saying this is one thing that I noticed is different. And so you might be wondering, okay, we've been doing gamma for precision, and how does it change, or what does it mean to give gamma to sigma? Okay, so this is something to keep in mind. And then another question I want to mention, I think, is I might have missed some question. I was reading the comments. But Hanshin also asked when to use hierarchical modeling. The video, I think, gave some justification. Many of you made good comments about it. So, yeah, once I finish writing those questions, I want you just to discuss with the neighbors very quick to get through those questions very quick. But I think many of you made a good point about why you want to do this in the particular case. And do you think you can start to generalize some, like say, some general guidelines of when you should use hierarchical modeling? Okay, so that will be what I want you to discuss about. And the third question I have, I think both Kevin in our class and Isaac is also from Swarthmore. They've been asking questions about, okay, we understand that it's nice to share those priors because we can share information, right? But at the end of the day, you are using fewer number of parameters. You could have used many more, but using fewer, right? I mean, the advantage of it is use, like sharing information. If you think they should come from the same priors, then why not? But they asked about the problem of if you are using fewer parameters, won't you have any kind of information loss? Okay, because if you have more parameters, you are fitting the, like you are giving more flexibility to the model, right? So if you're using fewer parameters, would that be an issue? Okay. So that's the third question that I saw from the post. And the last one that I thought will be specific to the video itself. I think Johnson asked about it, which is a question that I have as well. I didn't get it clearly from the video, is how to determine whether someone is a learner. They talked about it. I mean, Josh talked about it in the slides. I mean, in the video. But it was pretty quick. I still don't know exactly how it is done. And so if you have any ideas, feel free to discuss, and then later when we come back to you as a whole class, you can offer some of your ideas. Okay? So let me just like pause for like 5 to 10 minutes. You can go through those questions or any other questions that you might have. And I post the slides on Moodle, so if you have your laptop, you're welcome to open the slides that Josh prepared. And then at the end, after 5 to 10 minutes, we're going to just look at it quickly together. My plan is we won't go into like too much of the detail today of how the modeling is done, but once we cover what you can do about hierarchical modeling in general, we're going to go back to revisit this video a little bit to see exactly how things are done. Okay, because right now I think we have a rough idea that we want to share information across different groups, et cetera, and then that will be the good time for you to use hierarchical modeling. Okay, but exactly how it is done, it's unclear. And earlier today, I also shared Jack's script. So if you're curious, you can take a look. Just reading the Jack script, I think, can tell you how exactly the model was fit. Okay. But no hurry now. I think for today, hopefully we go through some of the key questions that we have. We might not be able to answer all of them, or any of them, I don't know. And then after a few lectures, when we talk about how you can do it using a simpler model, then we can come back to those questions again. So I'm going to pause here, and yeah.
Okay, I think
so before we go to the slides of Josh prepared. Anybody wants to comment on any of those questions? Or I mean, you can summarize what you have seen in the video, in the slides, and then offer some ideas about, say, especially like number 2, when to use hierarchical modeling. And yeah, for 4, like I don't know how it was done. I had a vague idea, but I'm not sure exactly. So if you have any idea, that would be good. Anyone? Yeah, question.
So I'm actually not sure how he gives the prior values for his hyperparameters. So you can, if you check his JAG script, he has like concrete values he uses to generate the parameter distributions. There must be some principled way he does it. It's just like not clear through this code.
Right. Yeah, and that's not in the video either. I think in the video and the slides, we know what priors was given, but we don't know the values of those priors, right?
Yeah, I mean, we use a lot of like hierarchical modeling and cognitive science, so we're trying to like draw this. We have this connection between group level data and like individual level data, and we want to explain both those trends. That's what we use. And the reason we kind of use these shared parameter values for these different kinds of things, and I think Josh talks about it a little bit, is that there's like some commonality in like what you're doing for all 3 kinds of key presses, right? And there's this tension where you want to build parsimonious models and avoid overfitting by having too many parameters. And that's kind of one of the reasons that goes into choosing the same kind of distributions for all of them.
Right, so there's certainly certain similarities. I think there are 3 conditions, right? The known words, the scrambled, what's the
novel.
Ah, yeah, novel words, yeah. So those conditions, I think, there are certain, I mean, they're fitting those normal model for all of them, and then they share all of the parameters. So I don't know if you I don't know if you noticed, but I realized so there are 2 parts of this video, right? The first part is, we're just going to model those average learning time or response time across different groups. And then that was the model just at the group level, right? And then later, the second part is, we also care about the individual level model, or like individual level data, we want to model that as well. So then hierarchical modeling is definitely used there. But if you pay attention to it, I think even the first half, it's certain hierarchical modeling as well. Because we're going to go into the slides really quick, but I think what they're doing is they have, 9 different curves, right? I mean, 9 different models, and then all of the alpha, beta, and gamma parameters are all shared. Okay? So that's itself a hierarchical model. Okay? Because what else are you going to do? If we are not thinking about any kind of hierarchical or sharing information, we're just going to have 9 different groups of data and fit them separately. Okay? But that's not what was done. So hierarchical modeling, I should mention, should now, it can happen even if you only have group level data. Okay? It makes much more sense, I think, later on when he went on to talk about, if you care about both levels, group level and individual level, hierarchical modeling definitely makes sense because you want to account for both. But even if you only have 1 level data, you can still do it hierarchically. Because if you believe across 3 different conditions, like the alphas and betas and gammas, they're essentially measuring the same thing, then you can share them. Okay? So that's I think important to differentiate. But then anyway. And information loss part, I think Cushing just now was saying you don't want to overfit the data too much. So of course you can design complicated models with as many parameters as you can think of, but there's a certain, I think, threshold that you don't want to overdo it too much. Because the thing is, especially if you think about why we're doing all of those models, like we have this data set and then we want to learn enough about it, and then some underlying features, or I would say underlying mechanism of how, say in this case, the learning happens. And then when you go to a different data set or a different scenario, you want to have, say, maybe not even go to a different scenario, just I want to make predictions, for example. Then if you overfit the data too much, then it's going to be too much tailored to the sample that you have, and that won't be as good as you have a simpler model. Okay, so that again, there's a whole lot of literature on how to do that. And anyway, good to keep in mind, like we want to strike the balance of how many parameters or how complicated the model is and how much we can learn about the structure. Last one, I mean, once we get to the slides, I can make a few more comments about my understanding, because my understanding of that is they do fit. So remember at the end, they have a bunch of parameters, like group level, individual level, and then they also have, I think, this probability for each group, not each group, each condition of determining whether one person is a learner or not. Okay? And I think that whole thing, the whole set of that goes into the model as well, because those are unknown. And I think it was being sampled across the MCMC. So I don't know for sure, and so let's take a quick look. So let's see. So this was nice, and let me maybe just. He talked about 3 different theories of this kind of learning, right? And then one of them, I think the first one, is talking about those smooth curves, right? That's why I think they're using a power function for that. Whereas the other 2 is it's like a abrupt jump, the step function there. So you're hoping to differentiate those 2. And then very interestingly, I think, because in the first part, when they're doing the average learning time, if you average over across the whole condition, then it's pretty smooth, right? So if you look at the average aggregated data, you might just want to use a power function, right? Whereas later, when you start to, so there was a slide, you will see it when you saw it before, that that kind of average learning, that red curve is being aggregated by all kinds of step functions. And each of that line is a individual response, right? So then that will be the time, I think, that they start to think, okay, we're not capturing that variability, we're capturing that feature of individual learning, so we should consider that as well. So that, very typical. Sometimes if you look at respondent level data, you see one story, and when you look at aggregate data, you see a different story. So that is typical of many kinds of statistical analysis. Yeah, so this is what I was talking about. And I think in the end, there's another plot about the red curve fit well for the average learning time, whereas the green step function is very typical for individual, and it's a bunch of them together. This was the, anyway, it didn't work, but I saw it before. It was just like going through, if it's right, you're just gonna type it, and then that box, if you type it right, I think it's gonna become green, and then otherwise it's wrong. All right, so these are the 3 conditions that they talk about, right? So these are obviously 3 groups. So at the higher level, you start to have the 3 groups, and then they record learning times. So my understanding is there are different number of respondents in each of those groups, right? And then you record the experiment. I mean, those are subjects, and then you record the response time for each observation. And then for the first part of the video was about the average number of learning response time for each group, and then the second part is individual levels. Okay. Yeah, and then of course, because of the pattern, in the end, they only looked at N and W, but N is, I think, considered as the, unpredictable, right? Because you don't know when it's going to happen. But once N starts to happen, it's going to be I, and then definitely going to be W. So they looked at N and W in the end as comparison of the learning style. So this is the average time, I think, and NIW, and because N is unpredictable, so you see that the learning, even so, it's color-coded based on different contexts, which is the condition that they define. So that's why in the left-hand side, you wouldn't see much of a difference. Overall, it's decreasing, right? As you get more familiar with the test itself. I think that's what they call like adaptation, right? Mm-hmm. And but then overall, you don't really see differences across different conditions. However, if you are doing I and W, then you start to see the differences. And it looks like the known words condition people like learn faster, right? Because you see a more decrease, or like the curve is more going down when you're looking at the response time. Okay? But again, all of this, I think, is the average learning. Okay? It's not for everybody, it's aggregated. And all right, so this is the fun part. I always like looking at those. And okay, so this was, I think, one of the curves that he was talking about, right? And they give a normal distribution for the response time, okay? And so that's the data model. It's not yet the prior or hyperprior, it's the data model. And we're, so far, I think, familiar with it. And it has a mean mu t and a sigma, standard deviation sigma. And they give a power function, it's alpha and then beta, gamma. All that together gives you the parameterization of the mean. And sigma, I think it's just minus 10 is shared across the different conditions. Okay? So specifically, they gave a gamma distribution for alpha, beta distribution for beta, and gamma distribution for gamma. And then sigma was a gamma distribution. Okay? There are certain terms, I think, maybe some of you know more than I do about this learning theory, because I think it was mentioning that alpha, I think, was the starting point of the learning, I think, the position, and the beta, I think, let's see, I wrote it down. I think beta is defined to be the amount of learning, and then like gamma is the speed. Anyway, I think it's about like how the power function is specified, and then it's probably very typically done in the learning setting of those materials. Okay? Anyway, so you can see that. So all of this are, so all of this are priors, right? Priors, and then priors. Right? So if we were to fit the data in each group separately, we're just going to have 9 different models, and then we only fit it within, right? However, they start to talk about, okay, because alpha and beta, they're all sort of measuring the same stuff, even though it's in different conditions. So they start to put the same beta prior for all of the betas. Okay? So that's why they say, so that's why they say they have NIW, each of them has 3 different curves, and then they give the same beta distribution. And then he didn't point out like for the alpha and gamma, as well, but we would imagine it's the same prior giving to all of the parameters at the same time. Okay? So this itself is hierarchical. So this is what I was trying to point out earlier, that even though we're working with group level data, it's aggregated, it's the average at the moment, but you are still doing it. We call it hierarchical because like at the bottom here is the likelihood. I mean, I should say the data model, right? And then you identify the parameters in your model. And then if you believe, say like all of the betas, the 9 different betas share the same beta distribution, it is hierarchical. Okay? And then similarly, all of the alpha goes from the first gamma distribution, so that's also hierarchical, and then gamma goes to the second gamma distribution, so that's hierarchical. Okay? Yeah. So the way to think about it is, if it's not hierarchical, you're just going to fit all of them separately. There is nothing being shared. Okay? Whereas here, I think they're saying that alpha, beta, and gamma are essentially measuring the same thing, even though people are grouped in different conditions, but it's measuring, I guess, the same, like the speed, the rate. I don't know exactly what they are, but that's what they believe. So I think then they put it hierarchically. Okay. All right. And I should mention, I think all of the sigmas here, my guess is they put the same prior distribution for it. It was never mentioned. I don't know. But I'm guessing is all of the same sigma is probably done hierarchically as well. and then they put a different, put the same prior distribution for that. Even though I don't know much about the setting or the context, but if I think about it, I might put separate sigma for different groups, just because sigma is now measuring the variability, right? It's possible that within N or within I or within W, they are just different, the variability. So I might put separate, like 3 different sigma priors for them, but it's still hierarchical. Here is 9 sharing the same for the alpha, beta, and gamma, but for sigma, I don't know. I mean, what they're doing now is NIW, so I might put sigma, the same sigma for all of the N's, all of the I's, and all of the W's. That's one way you can think about it. Another way is, because it's 3 in each group, because it's 3 different conditions, right? It's 3 different letters that they're testing, but then in each of this, you have 3 different conditions, because it's the known words, the novel words, and then the scrambled, right? Yeah, so alternatively, what I can do, if I just play around with the data or play with the model, I can put the same sigma for all of the same conditions, if I believe in that, okay? Or what's shown here is you can put the same sigma for different letter. It just depends. I think it's a great place to do some exploratory data analysis, just to see how data is being distributed within the different letters, and then within the different conditions, because that might be a hint of how you want to put the prior for sigma. All right, and then this was, I think, the results that we saw before, and then this is the plot that they mentioned that once they start to look at individual level data, they don't want to do that kind of smoothing too much for the average, and then they start thinking about doing hierarchical modeling for both. So again, where we covered so far is still on the average aggregated data, but it's done hierarchically. And once you start to think about the individual learning curves, then the hierarchical modeling makes even more sense. So this is, I think, individual level plotting, right? They were doing, so the predictable, I think, was the W, and the unpredictable was the N, because they're looking at those 2 letters only now. Okay? And then I think it was said that the first row, those 2, are sort of like they're blended. It's hard to tell. There's clear difference, right? If you just look at the plot. And the second row is you can see they're similar because the red and the green are blended well up to a certain point, like 40. And then after that point, you can see a lower response time for the predictable case. Okay. And then lastly is the red and the green, they even start differently, and then the whole trend is different. Okay. And I think it was the middle point, the middle row here, that I think they were talking about that particular function of fitting 1 and then multiply with that. Yeah. So that, again, I think that idea, I don't know, might be coming from this kind of exploratory data analysis. You start to see that you might want to fit a model like that. And then I think that's a good thing. Yeah. I mean, because if you just look at the data itself, for this one, you might just do 2 car curve, right? They're just totally separate. Yeah. And this as well. Whereas the first panel, well, we might just fit all of them together. I don't know. Yeah, depends. But I think plotting the data early on can give you definitely some ideas of how you can move forward. All right, and this was what the model was, right? Yeah, so my understanding of all of this is if you look at just how they parameterize everything, these are all shared, right? So this, I think we are able to read it from the JAG script as well, but I think it's worth mentioning. This is how I think this one, and this one. So they're essentially, I think, sharing all of them together. And so this is across conditions. And then even across different letters, right? Because it's the same here. So you can count, I think, how many parameters are there. Yeah. And again, I think he made a really good point about how you can think of this jump and how you're doing it with this multiplication. There are certain things about power function that I think I don't know well enough to understand, like, oh, why you can do this so you can change the general shape. But I can definitely, like, generally see what he was trying to say. But for me, the key information here is how the parameters are being shared. And then that is how the hierarchical modeling is done. Okay. And lastly, I think that was the result. And you can see, so I think it was this plot, I mean, this slide that got me a little bit confused about the probability of like classifying someone as a learner, because you can see on the top, they have an individual level probability of classifying someone as a learner or not. So that to me is adding how many number of observations there are, that's adding how many number of extra parameters. Because they do have this probability for each person to be a learner or not. Okay, so I remember the first panel it was saying is they are not classified as learners because you can see all of the probabilities are low, right? And then their outcomes are sort of similar, like, well, nothing changed that much, right? And the middle one, the middle panel here, those subjects, I think, have 50%-ish probability to be classified as a learner. So you start to see some deviation of the different words, the pattern. And the last row is everybody's classified as a learner because the probability is 1. And then you can see clear difference of how you might want to use the more complicated individual level model to capture the difference. Right? So that's my take. I don't know exactly how it was done, so I was hoping that the JAX script can be helpful. And then lastly, just really quick, one more minute. Lastly, this part, I think it was, he spent a few minutes talking about this. I recommend you to go back just to rewatch this part. I think it was really nice that he was discussing how this plot is telling us about the information of the parameters. Because this is a posterior summary. Okay, and we care about what? We care about beta, we care about gamma, we care about this omega, which is the onset of learning. And he was saying that you can see that for beta and gamma, like different conditions don't show too big a difference, right? Just by looking at it. So all of those are credible intervals. And the last one, you can start to see they're different. Okay, so those are important aspects to pay attention to when we're doing analysis overall. And you should go back to, I mean, not to this video in particular, but I'm just saying overall, when you do analysis, you should think about what the parameters mean and what the posterior is telling us about our understanding of the, say in this case, the learning features itself. All right, yeah, I think I'm gonna stop here. Sorry for overtime. And Thursday, lab 3 is due, so make sure you bring it to class. And yeah, that's all.